before we start talking about the proof, we need to talk about a few properties of conjugates. The first one being, if we take the conjugate of a real number a, that would be a minus 0I. And remember, a real number is essentially a plus 0I. So if we take the conjugate, it's a minus 0I, which leaves us with a. So if we take the conjugate of a real number, we get that number right back. Next, we want to talk about the conjugate of a sum. So the conjugate of a sum, so z1 plus z2. The conjugate of this sum is equal to the sum of the conjugates. So if I have a complex number z1 and I add it to another complex number z2 and then I take the conjugate, it's the same as if I took the conjugate of z1, took the conjugate of z2, then added them together. And similarly, the conjugate of a product is equal to the product of conjugates. So I can multiply a complex number z1 by another complex number z2 and then take the conjugate, and that is equal to the conjugate of z1 times the conjugate of z2. So if I took the conjugate of the conjugate of each one first and then multiplied them together, and it's the same thing. So now that we've talked about those properties, let's begin the proof. Now let's talk about the conjugate pair theorem real quickly, I guess, just so we know what we're looking for. We have some polynomial x, and when we put in some complex number z, a plus bi, we get a 0. So p of z is equal to 0. What the conjugate pair theorem is saying is that if a complex number in the form of a plus bi is a 0, then its conjugate, the conjugate of z, so that's a minus bi, is also a 0. So let's begin. Let's start by saying that p of x is a polynomial in general form. So an x to the n plus an minus 1 x to the n minus 1 plus a1 x to the first plus x0, a0. It would be x0 as well, but x to the 0. a0 is equal to 0. And when we put in z, so p of z, we get an z to the n plus an minus 1 z to the n minus 1 a1 z plus a0 is equal to 0. So what I'm going to do in order to prove this is take the conjugate of both sides, and if I can prove that they're equal, that this conjugate is also equal to 0, then I prove the theory. So let's start. Let's start by changing colors, I guess. So the first property, I've just taken the conjugate of both sides. Let's just forget about this side for now. I've just taken the conjugate of both sides. I've substituted z in, and I've just said that z is equal to 0. So I need to prove that this is equal to, so basically, hold on, let me undo that. So I have the conjugate, I hope everyone sees this is z. So I have the conjugate of z, but I need to prove that it's equal to 0 and it is also equal to the conjugate of z. So the first thing I'm going to do is use the sum property. So it says that the conjugate of a sum is equal to the sum of conjugates. So So that means I can write this like this. an z to the n. And this is still a conjugate. Plus the conjugate of an minus 1, z to the n minus 1, plus the conjugate of a1z plus the conjugate of a0 is equal to the conjugate of 0. Next, what I'm going to do is use the fact that the conjugate of a product is equal to the product of conjugates. So that will allow me to write this as the conjugate of an times the conjugate of zn. And now what I'm going to do is I'm just going to write the conjugate of zn like this. And it's the same thing. Plus the conjugate of an minus 1 times the conjugate of z n minus 1 plus the conjugate of a1 times the conjugate of z plus conjugate of a0 is equal to the conjugate of 0. Next, I'm going to use the fact that the conjugate of a real number is itself. And up here it says that if p of x is a polynomial function whose coefficients are real numbers. So what it means is that the coefficients of the polynomial are real numbers. So an is a real number, an minus 1 is a real number, a1 is a real number, a0 is a real number, and 0, of course, is a real number. So these can lose the conjugate sign, because if we take the conjugate of a real number, it is itself. So we now write this as an conjugate of z to the n plus an minus 1 conjugate of z times n minus 1 plus a1 conjugate of z plus a0 is equal to 0. Now if you notice, we have p of z, which is what we started from. We started with this equation p of z, and we substituted z, and then we took the conjugate of both sides. And now what I've just proven is that p of z is the same. If we substitute z in, that's the same as substituting the conjugate of z in, because this is the same as an x to the n plus an minus 1. Or let's write it like this. Let's write it out in a... Essentially what we've got in right now is p of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus a1 x to the first plus a0 is equal to 0. And what we've just done is we've substituted what we did originally is what we substituted in z. I took the conjugate of both sides, and we found out that if we substitute in z, that's the same as substituting in the conjugate of z. So therefore, the theory holds. It's therefore proven true. Because if I substitute in p of the conjugate of z for this equation, I get a to the n conjugate of z to the n plus a to the n minus 1 conjugate of z to the n minus 1 plus a1 conjugate of z plus a0 is equal to 0, which is equivalent to this.